Somebody want to take a shot at converting that equation into a word statement? Pardon? Okay, this is propane.
Yeah, propane plus oxygen is carbon dioxide plus water.
Okay, that's a noble first attempt.
Got one.
Okay, go ahead, Lex.
It's propane, right?
Propane.
Propane reacted with oxygen produces carbon dioxide and water.
Good. How would you say it then, Blake?
Wait, hold on, I had it in my head.
Propane.
Propane and oxygen reacts to yield carbon dioxide and water.
I accept either one of those, right? Okay. It's either propane reacts with oxygen to produce carbon dioxide and water, or propane and oxygen react to produce yield, same thing, X to produce or yield carbon dioxide and water. So that'd be taking a equation, be like taking a math equation and rewriting it as a word problem, or being able to hear a word problem and rewrite it as an equation. So as you look up here, you should almost be hearing in your mind propane. You may not know propane, but this one was given to you in the text. Propane and oxygen, or propane reacts with oxygen to produce. Propane and oxygen react to produce carbon dioxide and water. And I think our exercise yesterday, we were going to balance this, right? Didn't we end with this unbalanced? Right, we had not balanced it yet. So let's go through and do this as an exercise in balancing. For those of you that are in third edition, we are on practice problem, or excuse me, example, starting at the bottom of 230. The bottom of page 230, that's somewhere between 123 and 125 for second edition. We're going to go ahead and check this to see if it's balanced, and if it's not balanced, we're going to balance it. Okay? Now this is really our third day, maybe second full day. We had a part day 2 days ago. We worked on this. So we've had a day and a half of doing this already. As a matter of fact, I left this on the board, and yesterday Mr. Parker came in, and he was explaining how he'd already taught this to the 8th graders. And we went through it again to help him a little bit with his teaching technique. Okay, so you guys are kind of tracking just behind the 8th graders as they take the chemistry portion of their science class as well through this. So that should motivate you, right? Keep up with the 8th graders, you juniors. Here we go. Okay. Propane and oxygen react to produce carbon dioxide and water. What is the likely phase of each one of these? They're likely gases, right? We're probably, without giving any other word, we're probably going to assume it's at the temperatures and pressures that we're used to existing at and living at. And so we know propane at this pressure and temperature is a gas, and oxygen is a gas, and carbon dioxide a gas, and water could be liquid, but probably because of the three gases and energy going into it to produce the reaction, is probably in a more excited state, and this is likely going to be water vapor, gas. But we could condense back out, but it probably from reaction will end up being in vapor form. So I want to check this to see if it's balanced. What's going to be my first step, someone? With a hand. What's my first step? Yes. Okay, I'm not going to start with how much I have on the reactive side, but what do I have? What do I have on the reactive side? Remember, we're going to make this little matrix, this little table up, and we're going to start with what do I have on the reactant side? So, Lexi, why don't you tell me, what do we have on the reactant side here? So carbon, hydrogen, and oxygen. Okay, carbon, hydrogen, and oxygen. CHO. Good. You're right, CHO. Now let's go over and check the product side. Do we have all those same elements? If we have less or more, something's going on, right? We want to make sure that we start with and end with the same basic building blocks. So we have carbon, hydrogen, and oxygen on the reactant side. We're going to look to the product side, and let's go from left to right and just make sure that we have all of these and we don't have anything else. So we first see carbon. So I'm going to note that, yes, carbon is there. Oxygen. Oxygen is there. Hydrogen. Hydrogen is there. Oxygen. Yes, oxygen has already been accounted for. It's there. So all the basic building blocks, all the atoms on the reactant side are present on the product side. There's no more or less on either side, right? I mean, there's no additional or missing on either side. So now what are we going to do? Someone. Count. We're going to do an atom count on each side of the reaction sign. So I'm going to go ahead and make my table. Make one side reactants, other side products. You don't have to, but if you want to, you can put your lateral lines in here to form the grid. Now we're going to go through and do the counts. Let's count up. Let's start with carbons, and let's do the reactant side carbons. Going from left to right. How many do I have here? 3. One set of 3. I'd like you to do the sets and the number of each set. So look to the coefficient before the molecule. What is the coefficient? It's an implied 1. Carbon has one set of 3. And continue on the reactant side from left to right. Are there any other carbons? No, there aren't. So I do the math here, and my carbon count on the reactant side is 3. Left to right, my hydrogen count. Starting from left to right, coming across, what do I see first? One set of 8. Continue across, do I see any more? No, not on the reactant side. So I do the math. 1 times 8 is 8. This should be easy math, okay? This is kind of math that doesn't stumble us in chemistry, right? Maybe it's the easy math, right? We're not talking about rearranging formulas. We're not talking about anything like that. Direct and indirect relationships. This is just addition and multiplication. Looking left to right on the reactant side for oxygens. This is our first and only occurrences right there. And what do I have? One set of 2. Since I have no more, I can do the math, and I have 2 total. So are we done with the reactant side now? Okay, let's move to the product side. Matrix top to bottom. Carbons, going left to right. What do I have here? One set of 1. Now continue to look across. Do I find any others? No, I'm done. One set of 1 is 1. Hydrogens, left to right. My first occurrence here, what was that? One set of 2, so it's 1 times 2. Since there's no others, I can do the math here, and it's 2. Now oxygens, left to right. I have some here. One set of 2. Keep reading across to oxygens. Another occurrence here. One set of 1. So one set of 2 is 2, and one set of 1 is 1, and the total then is 3. So the first part of the question says, is this, you have to ask yourself, is this a balanced equation? It's not. Why isn't it balanced? Which of the numbers match? None of them, right? We've got 3 carbons on the reactant side and 1 carbon on the product side. That is not a match. I have 8 hydrogens on the reactant side and 2 hydrogens on the product side. That is not a match. And I have 2 oxygens on the reactant side and 3 oxygens on the product side. That also is not a match. So we're going to start balancing the equation. Where are we going to start? Is there someplace you prefer? Because again, I'm going to suggest that just like in math, there are lots of valid steps you could take. As long as the step is valid and you continue pressing forward, it'll work out. If you make an invalid step, of course, it throws the whole thing off. But as long as every step you take is valid, there are several different orders you can do them in and end up with the same answer. All right? So let's just start somewhere, and I'll just tell you what I like to do. What I like to do is look at where the product side is lacking. Okay? So I look over here, I've got 3 carbons over here, and especially look for those elements that only occur once. Which ones occur more than one time? Well, you look in all your boxes and find out where is there an addition that takes place. I can see from this that oxygen is the only atom in this whole reaction that occurs more than once, and it only occurs more than once on the product side, and it occurs 2 times because I have two multiplication problems here that I add together. Okay? So what I would choose to do is to not start with oxygen, because oxygen is in more than one place. But what I would do is start with something else, and I look for the ones that have more in the reactant side than in the product side because I can bump them up. So We've got 2 that fit that bill. We go from 3 to 1 in carbon, and we go from 8 to 2 in hydrogen. Somebody pick one. Carbon. Carbon has been suggested. For me to go from, how do I balance the number of carbons? Well, I have 3 reactants and 1 product. How do I end up with 3 in the product side? I go to the one place it occurs, right there, and I need to come up with 3 of them. How am I going to adjust it so that I get 3? I'm sorry, I knew you spoke, but I couldn't hear you. Add the 3 as a coefficient, right? The only things you can adjust, pound it in the ground. Remember, I told you at the academy, when the prof would do this, is something you have to remember. Here it goes. You only adjust coefficients. You never adjust subscripts. So we want to have 3 carbons in the product side, so I'm going to change this to a 3. Now, when I do that, I look at the entire molecule that I've just affected. I've affected the carbons, but I've also affected the oxygens. So I go back into my product side and say, okay, I didn't change anything on the reaction side, the reactant side. I have to look to the product side. The product side, carbons, I now have 3 times 1, which gives me 3, but I've also tweaked with something else, haven't I? I've tweaked the oxygen. Because when I take 3 of these molecules, I now, rather than having 1 set of 2, I now have what? 3 sets of 2. And 3 sets of 2 gives me 6, plus 1 gives me 7. It's off, but it's off even more now. But my carbons match. So my carbons are balanced. My hydrogens are not balanced, and my oxygens are not balanced. Okay. Strategy. Next one. You want to increase which one? Well, we're going to increase one of the atoms. So pick an atom. Hydrogen. Okay. So how are we going to go? We have 8 hydrogens in the reactant side, and we only have 2 in the product side. All of them are in this molecule. How do we end up with 8 with this molecule being the only one that's adjusted? Okay, so coefficient of 4 in front of the water. It affects my hydrogen, 4 hydrogen. My 1 set of 2 becomes 4 sets of 2, and the product there is 8. 8 and 8, it's now balanced, but I also affected the oxygens. As I look to the oxygens, 4 sets of 1 rather than 1 set of 1 gives me 4, and the sum there is now 10. So I've made the oxygen even more off. Okay, but I now have balanced carbon and I have balanced hydrogen. Now, I said that one thing I do is try not to tweak the one that has multiple occurrences until the end. Another technique, another trick to look for is as you look at the equation, find out where you have an atom all by itself. It's maybe a molecule, in this case diatomic oxygen. But you know what? When I tweak this, the only thing I affect is oxygen. And it's especially great when it appears over here, and it's the one that appears multiple times, because guess what? Now it's all just cleanup. Now let's go back and say, okay, what's off? Oxygen. Oh, beauty. When I mess this up, I'm not messing up any other atom counts when I change this coefficient. So now all we're left with is an unbalanced oxygen count. Looking up to my matrix, I have 10 on the product side, but I only have 2 on the reactant side. I need to increase my number on this side. That occurs here as the diatomic oxygen, the O2 molecule. So how do I adjust the coefficient so that I can balance with the 10 that are on the product side? Okay, correct. I add a coefficient of 5. That changes this to 5 sets of 2, which gives me a product of 10, and 10 matches my 10 on my product side to my reactant side. Oxygen now checks. And because this only occurs here, I haven't adjusted any other atom counts on my reactant side. And so the balanced equation for the combustion, you may not know it's combustion yet, let's just say the reaction. Propane and oxygen react to produce carbon dioxide and water. More accurately, we could say that 1 molecule of propane and 5 molecules of oxygen react to produce 3 molecules of carbon dioxide and 4 molecules of water. It's also true that 1 dozen molecules of propane reacts with 5 dozen molecules of oxygen to produce 3 dozen molecules of carbon dioxide and 4 dozen molecules of water. It's also true that, and stick any kind of unit you want in there in terms of a count number. This is 1 pair, 1 dozen, 100, 1 centa, 1/100th units. Let's say a bazillion. Let's make up the numbers. A bazillion. What's a bazillion? Hey, let's pretend we know what a bazillion really is. A bazillion, 1 bazillion propanes react with 5 bazillion oxygen molecules to produce 3 bazillion carbon dioxide molecules and 4 bazillion water molecules. Now I'm using this idea of the proportions and the counts so that later on when we start talking about the mole, and the mole is a unit of measure, of count, It's a unit of counting. If I say to you, give me a dozen, how many would you give me? 12. If I say, give me a couple, what would you give me? 2. If I say, give me a score, you give me 20. Very good. If I say, give me a mole, you would give me 6.02 times 10 to the 23rd of them. That's a huge number. It's so big. It's kind of like for now saying a bazillion. Later on, we'll be a little more chemistry savvy and we'll say a mole. A mole is like a bazillion of them, okay? It's 6.02 times 10 to the 23rd. It's Avogadro's number. And we'll become very, very, very familiar with this number soon. But for now, just as I said, 1 bazillion, 5 bazillion, 3 bazillion, 4 bazillion, let me put it out there in a way that you will become to recognize it very quickly, that 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. Yes, which is why we use it. The reason why we use a mole, and a mole being 6.02 times 10 to the 23rd, now this is outside the scope of this chapter, this module, but I think it's beneficial to say it right now, kind of led up to this. If I asked you to go over, if we had a pile of sodium over here on one of these lab tables, and I said, go over there and get me 1 molecule or 1 atom of sodium. We don't have instruments with the precision to do that. We can't do that. It's beyond our ability to do. I say, go over there and take a look at that 1 atom of sodium. I can't see an atom. We can't see atoms. As a matter of fact, even with the electron microscopes, the best we do is a computer-based algorithm that creates a visual image that represents 1 atom. Okay? But if I said, go over there and measure out 6.02 times 10 to the 23rd atoms of sodium, you would actually be able to do that with the precision of the instruments that we have. You could do that. It's so many of them that you can not only see it, it's so much of it that you can actually take the mass of it, that you can actually take a large sample of it and measure out a smaller sample and be able to figure out how many moles you have. And by knowing how many moles you have, you can multiply the math out and figure out how many molecules you have. Or in the case of an element, how many atoms you have. You're actually able to do that. Yes, sir. You may. Yes, you may. So, and another hint, again, outside, we're going to be studying this later as part of another module, but the reason why it's something that we can objectively measure is because it's based upon the mass of the element or the mass of the molecule. We've already covered atomic mass, right? So if I come over here and look at the periodic table and I see that sodium, atomic number 11, has a atomic mass of 22.98977 AMUs, atomic mass units. I can then take this jump and say, if I measure out, and I look at the mass of 22.98977, if I measure out that many grams of sodium, now a gram is something we can actually, we can actually see this now. We could take a whole bunch of sodium powder and we could skim off some and slowly brush it onto the scale, and we could measure it out until we have 22.98977 grams, not AMUs, same number, different units. Okay? Put that much mass of sodium on the triple beam balance, measure it out, and as best as we can do, to the precision we can do, measure out that much. When we have that mass of sodium, we then have 6.02 times 10 to the 23rd atoms of sodium. And we can do something with that. Because if I went through here, I could measure out 1 mole of propane and measure out 5 moles of oxygen based on the mass. And then I could say, what would be the mass of my products? Now let's think, concepts we've already had. If I said, for example, that this whole side of the reaction, the reactants have a mass of 150 grams. Just throw a number out there, 150 grams. Then what would be the mass of my products? 150 grams, because I can't create or destroy matter. I've got to have the same amount of stuff, right? Remember, I've got the building blocks over here. All I'm doing is rearranging them. I'm not making any more blocks. I'm not destroying any blocks. I'm just rebuilding them in a different way. So this reaction, whatever mass I have, the conservation of mass says, the law of conservation of mass says that whatever mass I have here, I have to have the same mass here. I can't create or destroy the mass. I'm going to rearrange this mass to look differently. And so I have a certain mass of propane and a certain mass of oxygen that'll produce a certain mass of carbon dioxide and a certain mass of water. The number of atoms or molecules, in this case molecules that exist, are going to be in the ratio of 3 to 4. And if I take the mass of 1 molecule, or 1 mole, and multiply it by 4, I would have the mass of 4 moles of water, and I can figure all that stuff out later on. So again, this will be on the scope of where we are right now. For right now, I just want you to see that one of whatever unit you count with, whether it be units, ones, whether it be couples, pairs, 2, whether it be dozens of 12, whether it be scores of 20, whether it be moles of 6.02 times 10 to the 23rd, one of those plus 5 of those of this produces 3 of this and 4 of that in whatever unit you started with. Moles, again, by count, not by mass, by count. 1 plus 5 produces 3 and 4. Any questions on that? Let me look at our answer real quick, make sure we got it right. 5023, yep, I wasn't concerned, but it is correct. Any concerns about how to figure out whether or not this is balanced? Any concerns at all? Any concerns then on how to balance it if it is not balanced? No? Okay. All right, if there are no concerns, no questions, go ahead and clear your desks. Blank piece of paper with your name on it, please. Blank piece of paper with your name, everything off, everything else off. It is. It is. Since there's no concerns and no questions, that means you're ready for a quiz.
Could you describe how much a mole is?
Can I describe it?
How much would it really be?
It would change. The question was asked, how can I describe how much a mole would be like, and the gesture was with size. That's going to depend upon the molecule or atom that, or the element or the molecule that you're measuring. Okay? The space of a molecule. Remember, it's a count. It's not a volume. It's a count. It's a count, not the mass. It's like I said, it's 6.02 times 10 to the 23rd. So if you had something that was very, very dense, very, very small in its molecule, it would take up a lot less space. If you've got something that's very big in terms of its molecular size, 6.02 times 10 to the 23rd of those would be big, but it may not have the same mass. It may be have a very low density. So it's variable. I mean, to say that it's this big or this big or this, you can't do that. It's how many of them?
It's usually something you can see.
It's at a volume that you can see, or if it's in gaseous form, it's at a volume that you can measure. Like if I said, okay, I'm holding a bubble of nitrogen here, you're like, I can't see it. Oh, but if I have some kind of containment field around it, usually in science the containment field is something called a balloon. Okay? If I know the mass of the balloon and then I fill it with the gas, and I take the gas over and I put it on the triple beam balance, and I subtract, I take the mass of the balloon and the gas, okay? And then I subtract the mass of the balloon, so then I have the mass of the gas, and then I can figure out the volume of the balloon, and now I have the density of the gas, right? Because I have the volume of the gas and the mass of the gas, and so density is rho is equal to mass divided by volume. So if I have this and I have this, then I can compute this. Now I know the density of the gas at this temperature and at this pressure. I can figure out how much of the gas I have, because there's a certain density per volume. It tells you, you've got the mass. So there's different different relationships that start to fall into place. But you can't say it's this big or this big or this big or this big, because it depends upon what it is. If I say to you, I would like you to pile a dozen ants over here and to pile a dozen automobiles over here, they're going to have different sizes. Well, how big is the dozen? Well, if I'm looking at ants, the dozen is like this. If I'm looking at the cars, the dozen is like this. It's huge. You're saying, well, they're very, very different. Yeah, but they're still both just a dozen. In the same way, 6.02 times 10 to the 23rd atoms or molecules. In some cases, it's going to be very, very small. In some cases, it's going to be huge. But if you were to count each individual one, you would still have 6.02 times 10 to the 23rd of them. All right, so we're clear, and we're just going to do on your own 6.9. It says that hydrogen and oxygen react together violently to make water. Hydrogen and oxygen react violently to make water. Write a balanced equation for the reaction. Write a balanced equation for the reaction where hydrogen and oxygen make water. Okay. You need a starter hint? I'm going to write a reaction. I'm going to write an equation, a chemical equation, where I have reactants producing products. And I'm going to write those reactants in their appropriate form. In this case, I have got two reactants that produce one product, right? Hydrogen and oxygen make water. I want a balanced equation for that. Everything we've done over the last 2 days. Okay? Okay, do your best. I'll take that into account. This is partially a quiz, but partially a pressured exercise. If you don't think you have any questions on how to do it, you're finding out right now whether you do or don't for yourself. Okay? So don't stress about the grade of this quiz. Just try to do it. You've got hydrogen and oxygen. I'll give her hints. You guys can listen if you want. So you've got hydrogen and oxygen reacting to produce water. You should know how to write every one of those in their basic form, okay? Not just their symbol, but how do we normally find them? So you consider whether or not each one is a homonuclear diatomic or not. And then write the equation, then write the matrix with all the different atoms that are in the reactant side. Make sure that all of them are included on the product side. There's no more, no less. Then go through to your atom count, just like we did on the matrix. Check to see if they're balanced. And if they're not balanced, start adding coefficients to balance them. Just give it your best shot. I'll let you know that yesterday's video failed. The program crashed when I tried to save the video. The audio, since I record the audio separately on a different system, the audio will be available for you to listen to it. And I'll go through and make some slides that kind of show what I was doing in class. You know, if you watch the videos, all of them this week have been posted, and usually it's just a recording of me up in front and seeing all my hand gestures and all that kind of stuff. This one's just going to be my voice, and I'm going to make some PowerPoint slides that kind of, because I refer to, see what we have on the board here? Well, I'm going to have to make a slide that shows you what we had on the board because you don't have the video to watch. So I'll be producing that as quickly as I can. Tomorrow is intended to be mostly labs, with some discussion after labs. With remaining time, I've already told Mr. Patty to plan on you being here for both periods, and it's part of his plan as well. And then Monday, review questions are due. Okay. Does anybody want more time? Okay. I'm enjoying the wake up at 5:30 routine I've started, but I don't like it at night. Man, I start crashing at about midnight. I can't stay up anymore. Last night I went to bed at 11. I got home at 8:30. You're going to bed when I get home from work, and when did you get up? Okay. All right, let's start walking through this. Keep your own papers. Hydrogen and oxygen make water. Somebody start me off. What is going to be my first reactant? H2, good. Hydrogen. Hydrogen is a homonuclear diatomic. It's going to come across as an H2 molecule, right? So I've got hydrogen and, so word problem, the plus symbol is the and. Hydrogen and oxygen. So my next, what should I write up next? My next symbol? O2. It also is a homonuclear diatomic. So H2 and O2 react to produce, or yield, those are the different words you may hear, react to produce water. The chemical formula for water? H2O. So we have an equation. Now, is the equation balanced? We can see right now that it's not very quickly because we have two oxygens but on the reactant side, but we only have one oxygen on the product side. So we can say, is it balanced or not? No, it's not balanced. Now the next step is, okay, if it's not balanced, balance it. So you may be able to start to get to the place where you can just do this in your head. That's fine. That will come eventually. Kind of like watching the Matrix. See all those numbers falling down. The guys that see it all the time, they see the images. For those of us that don't live in the Matrix, our systems convert that into images because we're more Mac-based. The Matrix is DOS-based. So let's go ahead and write down all the different elements that we see on the reactant side. It's simple here. We just have hydrogen and oxygen. So let's set up our balancing matrix. Reactants, products. Hydrogen, what do I have? One set of two and no others. So I do that, then the product is 2. Oxygen, same thing. One set of 2 to produce 2. On the product side, left to right, hydrogen, one occurrence, one set of 2, which is 2, and oxygen, one set of 1, producing 1. Now, you can't use fractional coefficients. What do I mean by that? I'm not allowed to come in here, at least I would encourage you not to do this. There is a way you can adjust for it, but I would encourage you not to come in here and say, okay, let me reduce this down to 1 by putting a 1/2 in front of this. Okay, let's make it bigger and then bring it down by using common factors of the coefficients. So let's start with this. I want to balance this. My hydrogens are balanced, right? My oxygens are unbalanced. I need to balance my oxygens. My technique, I look for what has fewer in the product than in the reactant side, and I up the product to match. So I have 2 oxygens on the reactant side, I only have 1 oxygen on the product side. So what do I need to do in order to use up 2 oxygens on the product side? Put a coefficient in front of the H2O of 2. That gives me 2 sets of 1, which gives me 2, which balances this. However, it also messes with my hydrogen, because now rather than 1 set of 2 hydrogens, I have 2 sets of 2 hydrogens to give me 4, and now my hydrogens are unbalanced. But now I have a greater amount in the product side, and I need to up my reactant side to balance my hydrogens. And just as I said in the last example, this is sweet because looking over here, my hydrogen that I need to adjust is all by itself. So when I adjust it, it's not going to mess anything else up, right? So I look across to this side and say, okay, I have 4 hydrogens here. I want to have 4 hydrogens on my reactant side as well. I need to have 4 hydrogens in order to produce 4 hydrogens in that molecule. So how do I get 4 hydrogens? I add a coefficient of 2 because that gives me 2 sets of 2. The product there is 4. 4 balances 4, and I haven't messed anything else up. So my balanced reaction is 2H2O plus O2 produces 2H2O. That's my balanced formula. Okay? That's my balance. How'd you do? Good? Good for the most part? Those of you that didn't get it, does this make sense? This is a pretty simple one, right? All right. Did you already use the back of your paper?
Yeah, I was writing it correctly.
Okay. No, it's okay. Go ahead and keep that one. If you want to keep what you've just done, that's fine. We're going to do another one to finish the class. Okay, we've got, what, about 8 minutes or so? Somewhere in there? Let's go ahead and give this one a shot. And I will take this one. Okay, I want to see what you do on this one. We're not going to go over it in class. We're going to go ahead and do the next on your own, 610. Yes? The O2? Why would it? I don't understand the question. I'm sorry. Could you say it again? Over here? Why would it have this? Again, I'm not understanding the whole question. Do you think you understand what she's asking?
I think I know what she means. She means like she doesn't understand why there's a 2 on that. Because it's oxygen by itself and then oxygen by itself.
It's a homonuclear diatomic. It's one of the elements that we learned that in its natural form occurs as a molecule. the reaction breaks them up. This reaction breaks up the bonds between these diatomics, okay, which makes it available to build something else. But if I were to put an oxygen atom next to an oxygen atom, they would bond with each other, you know, and you would have to use energy to keep them from bonding. They're going to naturally bond together. So if you have oxygen together, it's going to form O2 molecules. You're not going to stop it. So when I say oxygen, it's going to be in a molecular form. When you break it up and use it as a building block over here, now it's still in a molecule, but it's bonded with two hydrogens. It's in a different bond. Those are the ones. That's why I said before, when you write the reaction, look for, like it says, calcium and oxygen. You're going to go calcium. Well, calcium is Ca. Well, calcium's not a homonuclear diatomic. Calcium doesn't automatically bond with other calciums to make a calcium molecule. It doesn't do that. So when you say, I have calcium, it's a Ca. And it reacts with oxygen. Well, if you have oxygen together, it is going to form a molecule. So you're not going to have oxygen, you're going to have O2 molecules. So oxygen, if you have, say, I have elemental oxygen, single atom, I have a single atom of oxygen, okay, maybe. But if it says I have oxygen, assume it's a diatomic form. Nitrogen, hydrogen, and all those other column of elements. They're going to be in H2O2, you know, form. Cl2, they're going to form the homonuclear diatomic. That's one of the first things you check. When you look at the word problem, like in this one, it says solid calcium carbonate. Solid calcium carbonate is made when solid calcium, is it a Ca or is it a Ca2? It's Ca because it's not a homonuclear diatomic. When solid calcium reacts with gaseous oxygen, gaseous oxygen, and I know it's an O2 because oxygen is a homonuclear diatomic. It reacts with gaseous oxygen and solid carbon. Solid carbon. It's not a C2, it's a C. Carbon's not a homonuclear diatomic. So solid calcium, gaseous oxygen, and solid carbon reacts to produce calcium carbonate. What's the balanced equation for that reaction? Do your best with the time remaining and then turn those in as you go. Put them on the podium as you leave. I'm just writing the same thing below it a little bit more evenly stretched out, so I'm not changing anything. Yes? It's an S. It's an S. So it's CaS, O2G, CS, produces CaCO3S. Remember, what are the S's and the G's here stand for? Right, they're the phases. Solid, gas, solid, solid. I don't have an L up here, which would represent a liquid, and I don't have an AQ up here, which would mean aqueous, meaning it's in water. If you're concerned about how you do, it is on your own, the second to last on your own of the module, so you can check the on your own answers on your own.